told you that the marginal effect in nonlinear model is not unique. However, I'm showing you an output of marginal effect. It seems a bit crazy, but at the end of the day, it was not. Because the theta is forcing the marginal effect. Indeed, it just defined the other regressors as the average of other regressors. So the first derivative of u on over xi is going to be beta I times the cumulative density function for other regressors. However, theta takes the average of the other regressors and tells me the average partial effect. You can go. Okay. Now, we just run the predict code in order to use the test data and having PD hat, and we just defined some default classes that were able to help me for the destruction of confusion matrix. You can go. Okay, confusion matrix. Well, the guy, the last team described you the confusion matrix, so I'm not gonna go deeper in this kind of stuff. I wanna just underline something. Well, here. I decided to have a threshold of 5%, 25%, 50%, and 10%. Threshold are subjective. You can choose your fancy threshold and what threshold you like. And here I have the predicted default. So predicted default, predicted no default. Here I have the actual default. So yes, the guy defaulted, no, the guy didn't default. And remember, I know that because we had the performance data. So I know what at the end of the day is going to happen. Well, I predicted that there will be at maximum 4,640 default, and I was right, because that guy defaulted. But at the same time, I predicted that this guy are gonna default, but they didn't, so I was wrong. Specificity and precision, that are the index that the professor suggested us, are indexes that works on the no default side and default side. Well, honestly, we try to give our footprint to this project. That's why we created, or we try to create, is a kind of confusion matrix 2.0. You can go. This is our developed confusion matrix. And I run the predict code, and I use this fancy line code to have this one. Okay, how does it work? Now, I predicted the PD hat. So I used my probability modeling in order to predict my PD hat. And Stata was able to divide the PD hat in 10 bits. In each class here, 1, 2, 3, 4, and so on, there is the 10% of my PD hat. And there is also a grid intrinsic information, because here I have the 10% of the lowest PD hat, here I have the 10% of the highest PD hat. And in the body, there is the different shades of PD hat. After that, Stata compute the average in this bin. So taking 10%, the average is this, so 1.75%. Now, we try to develop the concept of turning threshold. Indeed, Stata is gonna compute, is gonna tell me how many people in these bins has a PD hat higher than the average. It turned out that there was 16 guys. So 16 guys had a higher PD hat than the average. And we did the same for all of the other bits. Well, it turns out that we expected to have at maximum 16 defaults, and at the end of the day, so in time t plus k, we had 18. And here we predicted to have 435, and we had 413. Now, when we work on this kind of stuff, honestly, we don't care about the tails, because here there is a huge probability of default, and here there is too little probability of default. So I care about the main value, which is 4, 5, 6, and maybe 7. Well, it turns out that for the 5, which is a 7% average PD hat, I predicted to have 80 defaults, and at the end of the day, in time t plus k, remember, when I say I expected to have, it means that I am in t. Someone asked me for a loan, and I predicted that at maximum there are going to be 80 people. Now, as Basilio said, the PD hat is an important information in order to compute expected loss and other stuff in order to have the exact risk-adjusted spread. So now, for the fourth class and the sixth class, we expected to have 106 default and 59, but we had 40 and 119. Now, as we know, in all of books, there is always the same statement. And this is the following one. Since there is no a specific trend we don't tend to systematically overpredict, and we don't tend to systematically to underpredict. This means it turns out that the likeness of this trend allows me for like a mutual separation, in the sense that if I don't tend to overpredict and if I don't tend to underpredict, the underprediction is going to be equally weighted by the overprediction. So it's a fancy way to try to get a nice meaning from this model. And as you can see on the non-default side, we were pretty always right, but it was not surprising because in our sample, just the 10% of the guys defaulted. So the 90% of the guys didn't default. That means that the 90% of 46,000 people, so something like 35,000 people didn't default. So I had a huge amount of data. This is the reason why our model was good on no default side. You can go on my last slide. Okay. We just use one measure of goodness or fitness, or maybe two, but they do the same work. Because when I run LROC prompt, I'm just telling you, hey, give me the graph form of the Gini's index. The Gini index is known all over the world as the inequality index. And the LROC prompt gives you this representation. When this curve tend to go here, I'm gonna be happy, because the closer is this curve to here, the better is my model. However, our LROC is not the best LROC in the world, but it doesn't look bad as well. Well, the Gauss-Miller of test is the main test that we use. The Gauss-Miller test is known in the econometric world because it's known as the equality of distribution test. The null hypothesis is that the no default distribution and default distribution are the same. Or at the end of the day, no default and default comes from the same distribution. As you can see, Ks goes from 0 to 1, and the p-value was straightforwardly 0. It allows me to reject null hypothesis. So I reject null hypothesis of equality of distribution. This in turn means that we were able to get the cut between the non-default distribution and the default distribution. Well, honestly, since the Ks is no higher than 0.60, there is still an issue of overlapping tails. So the left side of default and the left side of non default are going to be overlapped themselves. But at the end of the day, since our p-value is 0, we were able to get one of the most important meaning, that is the following one. As the last group described last week, we did like a linear discriminant analysis in just a few seconds, because if the p-value is 0, I was able to discriminate. But this is just what the linear discriminant analysis is doing. So we reject null hypothesis, and we were able to do that. After that, we had just some issues about the tails of distribution. And I'm really thankful for listening. Sorry for going beyond the 45 minutes, and thanks a lot.